just whenever you start presenting. Okay. And you can go ahead and set up your screen sharing if you want now, since you're the first presenter. Great.
Hey guys, am I audible and are you able to see my PowerPoint?
It all looks good. Preston, do you have your recording set up?
Am I audible?
Yes, we can hear you now.
All right, good afternoon, everyone. My name is Preston Rahim. I'm a junior in computer engineering, and this semester I decided to look into the task of generating 3D models from 2D images. So a little bit what we'll be getting into today, we'll go over some motivations that we have for why we would even want to solve this, a couple background information on concepts of rendering and rasterization that make this process a little bit easier to understand, what I tried to do with the model I found, how well I did, and how well it can be improved. So oftentimes we live in 3D space. All times we live in 3D space, but a lot of times we have to model that in a 3D environment as well. And we have an abundance of cameras and images widely available that allow us to extract data about our 3D world, but to be able to interpret that in a 3D environment, it takes a human to infer the depth of that object within the image. So we're really good at that, but getting a computer to do it would take the necessity of people to have to go in and look at a picture and then kind of have to guess on how far back it exists in 3D space. So common applications of this would be autonomous navigation for vehicles. Should they be able to see a car from an image from one point of view, they should be able to know how far back that car exists in 3D space and make proper driving arrangements for that. And rapid development of computer games, even in the entertainment industry. If you are able to take a picture of a landscape or a mountain and have that very roughly modeled in 3D space before you can go in and do the fine details, that very much speeds up the process. And just to have a tangible idea of what exactly this is, here's a snapshot of Purdue using Google Earth that uses exactly this technology. So using the satellite images from kind of funky angles where it kind of sees sides of the building, it's able to take an abundance of those and create 3D mappings of buildings that we're able to interact with. So some of the background info that we need to have before tackling this is the concepts of images and the concepts of 3D models. So as we all know, an image is a 2x2 grid of pixels, and each pixel has certain values that correspond to its color. It's the discrete grid, and this is what separates the rasterization from rendering idea. So whereas you have these discrete grid of pixels for images, and vector art, even vector 2D images or 3D models, are more mathematical descriptions of the shapes, colors, and contours that you're looking at. They're not these discrete array of pixels. So you can scale vector art and 3D models up and down as long as they follow all these mathematical rules, whereas the grid of pixels will start to look fuzzy and there's no explicit definition of where one shape ends and another begins. It's just an array of colors. And that's where the differentiability challenge comes in, because going from 3D to 2D is an easy process because we can scale that and then we can basically sample to create the 2D image from our 3D mathematical description. Now, inferring 3D from the second dimension is a little bit difficult because you need to pull information infer information about shapes, colors, contours, and lines. So what I found was SoftRes. It's a rendering pipeline. That's really the big chunk of this that gets plugged into any neural network that you see fit for it to use in, and it infers information about the image and creates a 3D model and takes an image from that 3D model, goes back and cross-references it from the initial image. So some results of my implementation, so I'm running out of time here, is this is an airplane that the model was able to create from a lot of airplane images by the ShapeNet dataset. And I opened this up in Blender on my computer and we were able to see it exists in 3D space. And some of my take homes were that oftentimes it's difficult to generalize this to a lot of different objects. And as soon as the objects start getting very wonky and unnatural in shapes, it also becomes very difficult. Are there any questions?
So I have a couple of questions prepared, but by all means, interrupt me if the rest of y'all have any of your own questions. So I see over here, you mentioned optimizing the network for performance. Do you have a clear inclination on how you would go about doing that to use this pipeline, that is? Can y'all hear me? Okay, I'm gonna type in chat.
Yeah, I can hear you.
I can hear you.
Is anyone asking a question right now?
Preston, turn on your sound.
So your audio is not
All right,
working.
I'm gonna DM him the question.
Have I not? My apologies.
Can you hear me now, or should I DM you the message?
Sorry, where is the toggle for that? I assumed by sharing audio and having my volume up on my PC that okay, so I'll just read. Yeah, I'll stop sharing screen. That might be a good idea.
Can you hear us now, Preston? Hello, Preston?
How would you go about optimizing the network to use this pipeline? So, as I mentioned, the big chunk of this is the rasterization and rendering pipeline. And as you're correct, the network that you plug into that I used was just what the researchers that developed this used. So going in and maybe changing the optimizer or changing the size of the inner layers might produce different results. Potentially going through different epochs, and tweaking those small little values to see if we can get higher accuracy on certain shapes. Yes, actually, I did find a different paper. One of the 3 papers I found did use ray tracing rather than the voxel-based representation. I believe the term they used was ray marching. It was developed a few years ago before the popularity of ray tracing in the entertainment industry became a thing, so they use a slightly different terminology, but it did end up taking calculations of how the light bounces around the 3D environment. It generalizes somewhat difficult, actually. So what we noticed was when we had chairs and benches that had holes in them, it got very, very confused. It did not like the fact that there were those slices and holes in our chairs from the beams in the back, and it did not enjoy those. But for solid shapes, it did pretty well. We scored high 70% on most objects in the shape not database. And looks like the professor would like us to move to the next person. Thank you very much.
Hi, can everybody hear me?
Yeah.
Yep, you sound good.
Okay. Okay. Hi guys, my name is Yuli Cho, and I'm here to present about MAST, which is MAST sequence-to-sequence pre-training for language generation. The difference between language understanding and language generation is like unlike language understanding, language generation aims to generate natural language sentences conditioned on some inputs, including tasks like neural machine translation and text summarization. Language generation tests are usually data hungry, and many of them are low resource or even zero source in terms of training data. There are a certain amount of data outside, so it is important to use the given data the most efficient way. And the original language understanding algorithms are not feasible since they are designed for understanding the given data, and the structure is designed to go through a single round per data input, which is not enough to get satisfying result. And here's a basic concept of MAST. MAST is a language predictor that gets a sentence with randomly masked fragment as an input and predicts this masked fragment. the masked fragments take turn and rotate, and the encoder part reads the source sequence and generates a set of representations, and the decoder estimates the conditional probability of each target token given the source representations and its preceding tokens. And the middle attention part helps decoder to predict well by finding which source representation to focus on. And it uses given data multiple times in multiple different forms, which is efficient. And here, MAST uses 6-layer transformer structure, whereas some other algorithm would use fewer layer of RNN. And what I mean by transformer structure here is, it is concept introduced by Burt research paper. And here's an example image of the transformer structure that Burt used. And mass transformers consisted of 6-layer encoder and 6-layer decoder with 1024 embedding hidden size and 4096 feed-forward filter size. Here's what I aimed for. The BLU score, the bilingual evaluation understudy score, represents how similar the machine could be compared to human. It compares machine translation and human translation in language. The state-of-the-art accuracy was 37.5, and it was expected to be reached through multiple epochs. Usually a single epoch takes about 2.5 hours. And here was a problem that I faced. The score reaches near 20 after 50 epochs and 35 after 100, and it took too much time and too much CPU usage. It would get better when multiple GPUs can be used at a time, but I could not have done it. So it was really hard. And here's a differing parameter that I actually changed. The K represents the number of the masked fragments of the given input language data, which is fragment length. The idea is that K grows bigger, the probability of the guess that the decoder makes gets lower at first. By looking at the BLU score after multiple rounds, K would go higher to make the information between encoder and decoder independent. And that is, decoder should be knowing the correct output when K is even equal to M, which is the total size of the input fragments ultimately. So starting from the ranging from K equals 1 to K equals M, it usually at first you start with the middle size, and that's when the best result comes from. Here's the other details. I got the data sets ready from XLM based English, French, English, German, English, Romanian language pairs. Data sets are transformed into specific structure called BPE, then put into epochs. Though the experiment does not show it, but fine-tuning afterwards increases the BLU score as well. And any questions?
All right, thank you. This is Flavio. I'm going to be the discussant, but
Yep.
Like my predecessor, if anyone has any questions, please do go ahead. Could you give us a couple of examples of how this gets applied to just end applications?
Like, what do you mean? Like,
how would this be applied to a translation application, for instance, if that would be the application for this?
Oh, so the basic idea is that this algorithm takes a finite number of information and use it possibly infinitely many times. So even when you translate, even when the situation that you're translating limited amount of information, and you have to actually like transform into complete sentence, it would still do it because it already has a database through the pre-training. So it finds the connection between the vocabularies. And even if when the sentences are like missing a couple of vocabularies, it would still find it and show better accuracy, a high accuracy. I mean,
All right, thank you. Sort of fills in the blanks. In your video, you mentioned that you'd like to apply similar, the same concept, but to images.
Yep.
How would that work? And you
So
said
the
you weren't
images-
very successful at doing that at first, right?
Yeah. So what I thought was that images are actually like consisted of single pixels. So by masking the part of the pixels, it would not like affect too much, but it would still miss some of the information needed. So by masking a growing number of fragments, it would successfully predict at final state. It would successfully predict, possibly, like the language transformer structure here.
All right.
That's what I thought, but I never tried.
Okay, that's a good project for the future. And just real quickly, what were your say top 2 challenges as you were going through the implementation?
Top 2 challenges. The one is that I already mentioned. The size of the data was too huge, and the single epic took too much, so I couldn't really reach the state of the art VLU score. And setting up the environment, that was another challenge I faced.
All right, let me open up if anyone has any questions in the group.
I believe we're out of time.
Yeah,
Oh,
we're out of time.
Sorry.
Yeah, can you stop sharing your screen, please? Thank you. All right. All right. Can you all see my slideshow?
Yep.
Yeah.
All right, excellent. I'm gonna speed through this a little bit because I have a lot to say on the topic. Please, at any time, just write a question in chat and I'll come back and answer it at the end. So my name is Eric Sibley. The topic of my AI project is self-training semi-supervised iterative networks. I know it's a mouthful, but hopefully by the end of this, that'll all make sense instead of just sounding like buzzword salad. So the motivation behind this project was the overwhelming dependency of training a network on a massive body of accurately labeled images. What happens when you need to train a network to solve a more niche problem? What do you do when you don't have this body of tens of thousands to millions of pre-labeled images to train on? If there were no labeled image libraries publicly available of cats, how do I train a network to recognize my cat cheeseball as a cat? This is the problem that this project seeks to solve. This project was inspired by the paper Self-Training with Noisy Student Improves ImageNet Classification. For those that don't know, ImageNet is an incredibly large image set that is frequently benchmarked, so it's a perfect target for this network to operate on, although it is hundreds of millions of images, so it's too large for my own usage. The premise of this paper was the same motivation of my own. The implementation was to use a pre-built efficient net model in varying sizes. First, an original teacher network is generated and trained on the training set, and this is the smallest generation. Then it places pseudo labels on a portion of the unlabeled set, assuming that these pseudo labels are correct based on confidence scores. However, the paper doesn't really go into the whole confidence scores part, which left me with a lot of questions and left a lot to be desired from this paper. As intuitive as a concept as it is, you need some kind of confidence metric to be able to confidently pass these pseudo labels down to future generations, which I'll get to in a second. Anyways, so places pseudo labels on a body of unlabeled data, which is our knowledge expansion portion, right? I'm growing the training set with each iteration. Then the whole program iterates. It generates a brand new student model that is trained on both the training set and the added pseudo labeled set, utilizing the cross entropy of both as the loss function, which again assumes that the pseudo labels are perfect, which isn't necessarily so. Yeah, so it keeps iterating. So each time a new generation of student is created, it's both larger and more complex than the previous generation. It's trained on the cross entropy of both the labeled and the pseudo labeled body, and it just keeps expanding our knowledge. So we have more resources available to train the next generation. Yeah, however, any misplaced pseudo labels create an incorrect bias during the training of the next generation. So my implementation. Well, originally I had found 2 other papers that I would like to modify and integrate into this noisy student paper to improve upon it. Instead, I decided to construct my own architecture of only the noisy student paper entirely on my own, which proved to be a daunting task. They simply imported a previously trained model named EfficientNet to use, while I attempted to re-implement their usage while building my own scalable network entirely myself. I began with the convolutional implementation, although I realized upon completing it that it could never be truly scalable, that I would always be limited by the pooling operation. Due to a lack of transpose operation, I always lose information throughout adding more and more layers, adding more and more complexity to each generation. So at some point, there's a generation cap, depending on the size of my input. At this point, I created a version that consisted solely of fully connected layers that works perfectly at all sizes, although obviously it became much slower as I generate a model with more and more layers. So effectively, while there's a hard generation cap on the CNN implementation, there's a soft computational cap on the FC implementation, if that makes sense. After run through training and testing, I run through an additional image set to test which photos I can add as an additional training set on the next generation of networks. More on this on the next slide. Evaluation. For the majority of my building and testing, the model appeared to perform absolutely terribly on my chosen dataset, the Street View house numbers. At some point during the testing of my extra set, I realized that my model always predicted ones, and upon further viewing of the image set, I realized a flaw. The original set is of multiple numbers, as the name implies, Street View house numbers. So I'm standing on a street, taking a picture of your house numbers. Well, that's multiple numbers, and it's usually cropped to one center number, which means you have a great deal of variance of numbers being on both sides. Also because you don't want to be trespassing, you're taking the picture from quite far away. So it's a very zoomed in, very low resolution image with very inconsistent lighting. So the result of this, because the majority of the image set is so poor, my network almost always predicted ones, and I nearly always converged to the exact same percentage of like 19 point something. I realized that's just the proportion of ones in the data set that I'm actually labeling correctly. So all I did was copy paste all the same code into a new Jupyter notebook environment, run on the MNIST set, instantly got 94% accuracy. So this proves that my model was entirely functional, but my training set was flawed, which I thought was educational, although frustrating. In conclusion, the network architecture works very well, but the application to the motivation is dubious. If we may assume that the network places pseudo labels on the extra set correctly, then we solve the problem of training a network on a minimal labeled set. However, this is not always a safe assumption, and further research in the area is likely needed to improve these techniques.
Hi, Eric. Great presentation. I was got a question. If a teacher becomes really confident at labeling something incorrectly, can any students down the line fix that?
So this is exactly what the motivation paper, or the paper that I drew my motivation from, tries to not mention as much as possible, or at least was my impression of it. The concrete answer is no. Once I've trained this bias into this training body, the training body will pass its bias onto the network being trained on it. However, I can do layers of pre-processing between generations of networks to try to remove labels with either low confidence or just poor labeling, but that consists of a human going through a massive body of data sets saying, this 4 was incorrectly labeled as a 1, this needs to be axed for my next generation to not have poor bias. So yes, but really no.
I assume we'll go to the late schedule, so I'll get one more question in. Would you attribute your struggles with the street number data set to the constraints of the model or just the quality of the image in the data set?
Definitely the quality of the images. The second, I want to say I only had 3 generations of 7, then 8, then 9 layers within each of those generations of convolutional layers, and they just immediately got 94% accuracy on the MNIST dataset. The reason I didn't further continue experimentation with the MNIST dataset is it doesn't have an extra body of unlabeled images, which I certainly could take a portion of the correctly labeled images from the training set and then use that as my extra set, right? But again, I suffer from how do you gain confidence over, or how do I create a metric of how confident I am that my pseudo label is correct without passing that bias on to the next generation. With the SVHN set, I chose it because it does have this extra set, and it also actually has the correct labels of them. So I can almost cheat in a way by double checking that my confidence is high and that the label is actually correct. That also, oh, next presenter. Okay. I think I answered that question. Any last comments before I stop?
Okay, just let me share my screen. There we go. Okay, can everyone see it?
Yep.
Okay, great. So hi, my name is Jackson Sanders, and today I'll be talking about my work in object segmentation via image perturbation. There we go. So to quickly, before we start, I'll define the problem as well as the motivation. So object segmentation is something straightforward. You have to extract the region of interest from an image, and this is a process of image analysis. Typically, it is done supervised, which will help refine or like at least start the networks on a whole bunch of pre-labeled and pre-masked images. Though the problem is that's very time consuming. And if you want to generate large sets of images and masks to help work with or for any other purposes you have, that's necessary. Can someone mute themselves? There's a lot of background noise. So to overview the implementation, I decided to re-implement emergence of object segmentation in perturbed generative models, which is a paper from NeuroIPS from 2019. The difference is I could not find the code anywhere, so I kind of had to start from the ground up. And for the implementation, I worked with just one type of set of images, which was the Caltech birds repository, which had like 14,000 different images of different breeds of birds, as well as the significant challenges that face in the implementation will be discussed later, but there were numerous ones. So to give an example of object segmentation, you have this original image of a bird here, and you can have the mask, which is simply a binary yes or no for whether the object is region of interest for the object. Then you can extract the foreground from it, and then you have the background, which has been kind of repaired using a blurring algorithm to try and make it seem like the object was never there in the first place, which we'll get into in just a minute. So the question is how to segment an object without supervision. It's a process of refinement and training. Cannot begin without a data set composed of pre-segmented images. So before you can start training any masks, you have to first, it's kind of like a chicken and the egg problem. You have to at least be able to segment them in some way before you can start refining the process. And because of that, I started work with a pre-trained network as a seed for mask generation, which then would theoretically be refined across iterations. So to give an example from how the paper did it, you can see there's three sets of processes. One where the mask is the whole image, one where the mask is, one where the mask is kind of surrounding the car, nothing. Then the mask is also non-existent. And then the third is the mask is perfect. For the foreground, it's either everything, noise, or just the car. And you can see when you combine those 3 sets of images and then you translate the car, you can see differences from quote unquote correctness in the image in the composite / shift. So feeding these segmentation flaws back through a neural network improves the generator, as comparing to the baseline foreground, it can figure out what is off and what shouldn't have been moved. And so dealing with perturbed image generation, these are kind of some data sets that I produced myself, where you can see you have the original image, then you can have the background, which has been repaired in a very quick and easy way, just using a Gaussian blur, as well as then perturbed for it was shifted. So I re-implemented a generator to produce real or fakes images, very simplified infill algorithm. Here's a process that the paper used, where you had to take the image in into an encoder, and initially just encoded a basic mask. It refined it, spit it out, compared on the D section the differences between, and then fed it back in again and again. And once the mask got good enough, they would start testing it and comparing between the baselines. The failings is that I tended to repeat asymptotes of the mask reaching the whole image itself rather than the object. Or sometimes when I cut it halfway off, the accuracy fell within 10% of 50%. Typically it was like 1 or 2%. And I felt that that was no better than random chance, whether it was able to guess that it was a real or faked image from the set. Future work, I would like to try a second attempt at re-implementing the encoder using more diverse data sets. Additionally, it was a lot of time consuming, but the problem is you tend to lose data the smaller the images get. Any questions?
Hi, this is Fong. Yeah, just like previous, if you have another question, please chime in. So you mentioned in one of your slides that the generator can produce a real or fake images of an object. Can you explain that a little more?
Yeah, so I forgot, I didn't have time to put it in this presentation. As an experiment, when I was having issues with the masks itself, I decided to recombine different sets of backgrounds and foregrounds to try and create faked image sets along with kind of scaling of them. So that was more just a process of trial and error to see if I could tell the difference between it or if I was actually repairing the backgrounds correctly. That was recombining different sets of different images in order to try and produce new sets of images. And then I fed those through again to see if there was, if the algorithm I was working with could actually detect and mask them correctly.
I see.
Yeah.
Okay, so given that, so let's say you have, you fit in the real image versus the fake image. How do you track the loss? Like how do you compute the loss so that you know which, how the generator performs?
It was basically, did it determine the right sort of mask? It was a simple one loss function of comparing the original background versus the background of the correct background from whether it was a real or faked image with the background upon perturbation for when it was shifted. And then the mask reapplied with the translation to see whether or not it was able to only cut out the object rather than the whole image.
Okay, thank you. Yeah, given the time, I think I'll just give it to the next presenter.
Any other questions? No more questions? Okay, I'll leave it to the next person then.
Hi, can you hear me?
Yeah.
Okay. Hi, hope you're doing well. It works is by, sorry, that. Okay, so my paper was about translating brain signals into text using a neural network. And the reason this would be useful is in cases where people have trouble speaking, as well as to have a general understanding of how our brains work when we communicate. I would imagine it'd also be useful for like future, it works. Oh my God, sorry. Okay, I'm very sorry about this. So my my project was about translating brain signals into text for the purpose of helping people who can't speak communicate, as well as have a better understanding of our brains help us in communication. And the way it works is that firstly, there would be patients with electrode grids implanted in their brains. And in this case, it was patients with epilepsy who were treated with ECOG, which were treated by implanting ECOG into their brains. And these signals are very large, and we're using an LSTM. So these signals are filtered and downsampled using this temporal convolutional network, and it's turned into feature sequences, and it's fed into this encoder and decoder. And so the encoder changes it into an abstract representation, and the MFCC is predicted so that it could optimize this encoder. And then it's fed to the decoder and turned into text. So to implement this paper, I used this repository on a Colab notebook. And so initially the paper used a parallel transfer learning, but because I was constrained with memory, I wanted to employ sequential transfer learning so that I could see like the output of one participant before I moved to the next. And the paper used 4 participants, and the repository is organized for the first 2 data sets. And the data set that I received from the authors upon request was for the last 2 participants. So I had to make changes to my YAML file for like the parameters of the respective patient, and as well as for the JSON file to adjust to the files that I have. And after that, I ran it on the last participant, which is participant D. And so you can see here that on the 180s epoch, there was like 100% accuracy, but this should not be surprising because the way the author used this training is that he only tested it on the first MOCA set, which is like 50 sentences. So it's not really that surprising. As you can see here in the 80s epoch, there's like a 98% training accuracy. And in this case, this is the validation accuracy. And so this is trying to do transfer learning. So it's like validating on the same training set, which it's basically overfitting. But you can see that even in the training set, it's doing a good job. But then again, it's using just 50 sentences. So improvement, there's room for improvement. And also you can see here that to see the significance of this temporal convolutional network, I want to, like the paper mentions, this is a very important part, and I didn't see it in other NLP papers. I mean, this MFCC is present, but I didn't see the temporal convolutional network. So I wanted to see the significance of that. And when I trained it without the temporal convolutional network, there was a lower accuracy rate. And if we employ this temporal convolutional network, though, we would get like a 0.54 accuracy. And also I wanted to see if like the ADAM optimizer was like the best suited for this task, because this NADAM and ADAM W were like, they seem to have hype. But when I tested that, I had a lower accuracy of 0.51 for the NADAM. And I would attribute this to the fact that the NADAM is better suited for like noisy data sets, and this one had like, it was filtered and downsampled. So I guess the ADAM was better suited for as opposed to the rest. And so as I've mentioned, I've used transfer learning, like the sequential transfer learning. And you can see that without this transfer learning, the accuracy would really drop. And here you have like a 95%, whereas here you got like a 77%. And my evaluation would be that this temporal convolutional network is very important in this task, and that the best optimizer is already used, and that as I've mentioned, there are like 4 participants, and this is very low, but you can employ transfer learning to solve this. And a possible future direction would be the use of transformers in this task. So because this used an LSTM, and this is almost like dead, and so a transformer would be like the future direction. And I would also like, as a takeaway, I would recommend reading this paper and seeing how it works. Yeah, thank you very much.
Hi, so I have a couple questions. So first, I'm curious what the data set looked like for this. I'm not
Sorry, what?
like I'm curious what like the brainwave data kind of looked like.
Okay, so you can hear me, right? So it was a TF record. It was a set of TF records, and it had like three datums. Like it had the ECOG sequence, the ECOG sequence as the encoder input, and it had the decoder targets. And then yeah, so it's using those like the ECOG signals, the ones that is found from the brain signals that from the patients, and then what you would like the decoder to like output. So in this case, it was like it used MoCA data set and a picture description of words. So that's what it used. Does that answer it?
Okay, got it. Yeah, and then could you explain the MFCC again, like how that relates? I was curious about that, and like what exactly that is.
Oh, sure. So the MFCC is a sound processing coefficient. And in this case, it makes like predictions of the sound of like it makes predictions of like, so there's the normal output of the like when the person speaks, and then there's like the one that the encoder gets, right? So it makes predictions of what the encoder input sound would be like so that it could optimize this encoder part. It's not like an essential part of the like of the translation, but it optimizes the encoder. So yeah, that's what the MFCC is. It's just a sound processing coefficient.
Okay, gotcha.
Okay. Any other questions?
Okay, I can finish mine then. Thank you. Let me share my screen. All right, can you see my screen? I should probably check the messages chat.
Yeah.
Okay, cool. So today I'm gonna be talking to you about my research I did throughout the past month on the use of Taguchi orthogonal arrays and their use in experimental design and how they can be useful for use in preventing bias in artificial neural networks. So one of the motivation of this problem is in data science, there's a lot of bias in data sets because we take whatever data we can get. We're just trying to get as much data as possible to characterize an outcome in a world of interest. And trying to make sure that all of that data is unbiased is easier said than done. So I was interested in the specific number theory topic, which is based on the idea that for any two variables in an experiment, so here P is a variable, if you look on the right, you can see that two variables are enumerated for all of their possible combinations you could expect for their value. So if you had two variables with four discrete different states that they could possibly ever be, then you enumerate all the possible combinations between those two variables. And that allows you to characterize the relationship between the two variables in that world. Now, the problem with doing this is if you wanted to do that to characterize your results for all of your variables in your experiment, the more variables you add, the worse your network performs because it increases at a factorial rate. You have to multiply. If you were to enumerate for all these five factors on the right, you would end up with 4 to the 5th different tests you would need to perform to test all possible conditions in a world. Whereas a Taguchi orthogonal array allows you to model all of the interactions between all of the variables in a minimal sense. So you're allowed to, it's a reduction on the number of tests you need to perform in order to accurately characterize a model, which is extremely valuable. So one of the problems I had with this was it was limited because research in the past had only really defined how to create fixed length and fixed size versions of these arrays, and they were largely handcrafted and used by the industrial engineering discipline as well as the mechanical engineering discipline to do research. And it actually was used widely before as a AI of the industrial engineering and mechanical engineering of the 90s and 80s. So, but I decided, unfortunately, to try to generate these all on my own, which I ended up not succeeding in doing ultimately, but I proved that it was possible, and I was able to create a fractional factorial design that was nearly the same length as a full factorial orthogonal design. I did not have enough time, but if I had the time, I was going to demonstrate how you could use such an algorithm. And this is credit to our professor for the suggestion, but to vary the different types of noise you can introduce to image data and compare the results between an image super resolution algorithm that was not fed various types of noise strategically placed in the data set versus one that is just normal. And I was planning on trying to prove that you could train it faster and get better, more accurate results quicker. The way that these models are evaluated are for super resolution is to analyze the bicubic upsampling. So you essentially just take the image and kind of just increase it in size and replicate pixels. And then you compare that against what one of these algorithms can do. And it's somewhat of a qualitative analysis. Even in the paper, they kind of show you all of the pictures and explain that one has less blur than the other, and they explain the specific artifacts, and there's an ablation study. So the idea was to perform all of this, create an orthogonal array, force these different types of testing sets into my algorithms to hopefully create an unbiased training set to all the different types of noise that I could see on an input image from a camera. So again, I was able to prove that, I mean, you can see the equations there, that if you take any given factor, if you take the number of interactions for every single factor in the experiment and that you need to satisfy, and you take the greatest common denominator of all of those factors, then you know the length, the number of tests that you need to perform in order to satisfy all of these properties. And it also tells you R, which is the number of repetitions that you need to perform for a given one of these arrays on the right. So you might need to repeat it a couple times if, for say, you had an 8-level factor in this experiment. In that case, you would have to have 32 tests to satisfy the constraints of the 8 factor, because 8 times 4 is 32. I mean, you would literally have to enumerate all of those possibilities. So you can see how, as you add different factors and levels, the nature of these arrays changed. And previously, it had been largely unknown how to figure that out. Unfortunately, again, I failed to get it done in time, but it was a journey. But thank you. My take-home message is look into experimental design. At the very least, just try and take a look at it, because it's a really interesting topic and worthwhile to try implementing it in future AIs. Thank you. Do we have any questions? I could probably go back to.
So on the discussion, what is unclear was that how these orthogonal arrays, like, can you say more about orthogonal arrays? Like, my understanding of Taguchi is like this quality monitoring, right?
Mm-hmm. Yes.
Okay.
So this is widely used in the automotive industry for quality, and actually is probably the reason Toyota has the quality reputation it has today, because what they did was they would, for all of their products, they would run a sequence of tests where they were modeling the intersection between the states of the variables. So they're essentially trying to say, what is correlating to the best outcomes? Is it this combination of noise with this combination of noise, or is it this and this? And you can do that because you're guaranteed a sample for all of the different enumerations of all of your variables. So you can build bins on these intersections between your variables and be able to accurately characterize the correlation between your variables in a minimal way and that's hard to do when you have a data set that is biased in a specific direction, because you might not be able to characterize the edge cases as well as the ones that you have more frequent this data.
Okay, so it's making it like an optimization, right? Is that what I'm understanding?
It's balancing the representation of all scenes possible in the world that you define in a set theory sense. Like if you define that if your outcome like, for example, if you're trying to eliminate racial bias, if your outcome is to be able to have the same accuracy for all races, you would want to represent all races equally. And this array allows you to design a testing set to feed your model that would guarantee that. So you could at least say to regulators, hey, I did train it with exactly the number of testing data pieces for every single type that I was supposed to.
Okay. Okay. So what would you feed to it to get the best like arrays?
So
Yeah.
so the best arrays are ones that are of the same power because of the principle of the greatest common factor. That's kind of the limiting factor, because when you have to think of it as how many of these different enumerations do I need to satisfy to make sure that this variable's interaction with all the other variables in my model are accurately represented. And in order to do that, you need to, it's easy to do that in a more elegant and information dense way when you've got factors that are all the same level. But it also causes what traditionally has been done is people have just they've duplicated elements. So if they only had 3 factors, they just repeat one, but then it's an unbalanced representation. So I didn't really like the idea that you couldn't create a perfectly balanced array that represents everything with at least the same number of samples.
Okay. I think we're out of time.
Yeah, that's so. Thank you. Oh, how do I stop? Stop. Sure.